Hello and welcome to our webinar about static performance estimation for timing analysis in early development. After the introduction of the topic, I will explain the static code analysis that is done for the performance estimation. We will talk about the benefits of this approach, mention the limitations, and finally integrate it into existing workflows. And to end everything, we will demonstrate it inside of our tools. What do we mean by early development stages? So first, let's have a look at the application development. The usual way is to focus on the actual functionality of the application. So you model your behavior inside of a Simulink model, for example. You write it in scripts or use source code directly. The goal is to test the algorithm and verify that the function is correct. This development is not always intended for the actual product. So if you start with a model, this is really only to check that you get the correct results. Only in rare cases, the optimizations for performance or efficiency are already done at this stage. Looking at the target platform, so in early development stages, there are different scenarios. So in some cases, the platform is already selected, a specific processor on a specific board. Sometimes there are decisions open between a few different alternatives, so the final decision is not yet made. And then there is also the case that an evaluation board might not be available. So a platform is already decided on, but because of some other issues, the board is not available. Now, what is the actual issue? Well, if you focus during application development or only on the functionality without taking the actual platform into account, this might cause problems later on in the development. So it could be that the timing is not met, so something that is usually detected during the integration of the whole system, or that the algorithm cannot run efficiently on the hardware. This means either there is not enough memory, or because there is no floating point unit, the actual implementation might be much slower than anticipated. And lastly, the detection of critical parts during runtime can become quite complex, so doing it early on might lead to an easier case. So really, what is at stake here then? So the costly changes to the code at the integration phase. So if you make any change, if you have to make changes during the integration phase, it's usually very, very costly because you have to go back and re-implement a lot of stuff, or you have to hire maybe external staff to look into the issue. It's also quite inefficient to find the high runners in the project if you are very late in the project. Now, if you don't have the actual timing during the application development, you might need to do a lot of additional profiling and measurements after the application development just for the integration to provide them the information. If you have this information earlier, you can already use it to plan more about the timing budgets and stuff like that. And lastly, about the platform. So the performance impact of switching the platform might also be unknown. So you just know, okay, you switch to a new hardware from a different vendor. How much do you benefit from it? So yeah, it's a faster processor, but maybe it has some other changes. Then it might be hard to estimate the performance impact with this switch. So what is the solution that we propose? It is using static performance estimation. So you can get the timing behavior of your application very early in the development flow. You can find the hotspots that use most of the resources also during the development of the application. And
you can already check if your application fits into the allocated time slots. Maybe a bit about where this fits into all our tool environment. So in this view, we have it here right in the middle, performance estimation. The idea is we have different tools here for code generation and conversion, maybe from MATLAB to C, C++ to C. And we have tools for optimization, and this performance estimation is here in the middle. It's an analysis part, can do performance estimation and dependency analysis. So this information is usually used to guide optimization. So either with our tools here, or if you want to optimize it during the development by yourself. Now, what is static code analysis? First, what we need is we need the execution frequency of a block. So how often is a block of code executed when running the code? This is usually not depending on the actual target platform, but this depends on the actual application, might have some dependencies to the input data, to the current state of the system, but usually usually it doesn't depend on the actual processor. And for the execution time, to get the actual runtime or duration of a program, we need the execution frequency multiplied by the execution time of each block. So execution time here means how long does it take to run this piece of code on the actual target platform. So this is highly target dependent. If we have a different processor, it might take twice as long, half as long. Really depends on the architecture of the processor. So how do we do that statically? How can these values be estimated? Let's start with the execution frequency. Execution frequency is usually affected by the control structure of the program. So for loops, while loops, do while loops, also conditional blocks like if or switches. And loops usually increase the number of iterations, and these conditional blocks usually are less than 1. So if we don't know anything, maybe 50%, or here even a different distribution. What we usually are interested in here with the execution frequency is the absolute count. So the total number of times a piece of code is executed during runtime. So could be 1000 times, and a relative count. This gives the number, how often is it called in comparison to the parent. Let's have a look at the example. So if we have a for loop here, this for loop might be executed once. So this means that the whole loop or the whole structure here is executed once, but the body of that loop is executed multiple times. So depending on this condition, smaller function or return value of a function. So could be 100. So we have a relative number of 100. This is just to give us a feeling of how important or how big the actual loop is. So this is the relative count that is relevant here. Usually the absolute count can be calculated then from the relative counts that are that are extracted. Now, how do we get these numbers? The simplest case is statically analyze this. Okay, we have a loop like this, then it has to be 4 iterations. So if we just have from 0 to smaller 4 iterations, if we don't have any changes to the variable I inside the body of the loop. This would be the simplest case, but usually this is an exception in normal code. Another thing would be constant propagation. So instead of having a fixed value here, we have a function call, or we have some kind of other calculation. And constant propagation now means there are some constants defined inside of the program, and we know what the function does. So in this case, we know, okay, the maximum from A and B, that would be 5. So it's replacing these functions with constant values. This is called constant propagation. This is something that can be done for a couple of cases. What comes to mind are image processing algorithms, where usually the size of an array of the image is somehow defined with defines inside of the program. So we know how many pixels we have in X and Y direction, and these values are used in different places, and using constant propagation, we should be able to calculate the sizes of different things, or the execution frequency of loops. If all this doesn't work, for the static code analysis, we need some kind of value. What we do is we use default values. This can be configured by the user, but typical values are, okay, we have an if block. We don't know how often true and false is executed. Then we just set the probability here to 50% for true and false, just to have an equal distribution here. And for loops where we don't know the iteration count, we use 10 as a typical number. Why 10? Well, 10 just, so if it's a loop that does really some processing, just multiplying it by 10 will make it at least larger than the normal processing part that wouldn't be done inside of a loop. These numbers here are, of course, not really reflecting the execution on the hardware, but they are useful if we want to compare the results relative to each other. So if we make some code changes and we see, oh, it became 20% faster, even if we use these default values, this 20% faster should be an indicator of the direction our optimization or new implementation goes. What are other options? Domain knowledge is something that is very useful. So if we really know, or if we just know what a typical case is, so for example, if we have in the code a while loop, queue is empty, then basically wait. What we are interested in with the static performance estimation is to get the typical case, so average case, and the average runtime. And for the average one, we can assume that the queue is not empty. We are interested in the part where, well, there is something in the queue and we probably want to process that or react to a message, something like that. So with knowledge about the actual program, there are a lot of cases where we know, okay, this should be, so for the case we are interested in, we should use value 0, or we should use, I don't know, value 10 because we send 10 messages, or we have a delay of that on our messaging system. So with the domain knowledge, we are able to provide these numbers externally. So this input from a developer, in our tool, we have several ways to do that. One would be to add these kind of pragmas into the actual source code. They basically define the absolute and the relative number of executions. In this simple example, for the inner loop, we know that it's executed 4 times, so this body. But here, this 68, we wouldn't know that just by looking at the function. So we don't know. So statically, it might be a case where we cannot analyze how often this is executed. It doesn't have to be inside of the source code, so we can also specify that in an additional file to not really have to make changes to the actual source code. And another thing to get more useful values here is to use profiling. Well, as said, we are doing static source code analysis. Static source code analysis means we are not executing the code, we are analyzing the actual source code. And well, profiling is would be executing the code, but we can do it on the host platform. So here directly on my Windows PC, and yeah, or why not on simulator, different hardware. So the target system is not actually required. And as we are only interested in the execution frequency, this doesn't really matter. So as I already mentioned, the number, this actual execution frequency is not depending on the target platform. But in order to be able to use the profiling, we require runnable code. Everything else I mentioned before does not require the code to be runnable. We can basically analyze the code. We have the sizes. We can analyze how often everything is called inside of that function, but without executing it. We need to be able to compile the code. This means we need to have all header files, all data types, all variables, all functions need to be available for our analysis in order to give useful values here. When doing profiling, it is important that the input data is representative for a typical use case. This means if the application depends on special data, we need to provide this data for the profiling run in order for us to extract useful frequencies here. Okay, let's move on to how do we analyze the runtime of the code. So we have as first option to analyze C code. It is fast, but not so precise. The idea is we look at the actual source code. So here we have a C program, and we look at the instructions that are there. So we can see there is an addition, there is a multiplication, well, there is a loop with comparison, addition, here also an addition. So we know what kind of instructions there are. And now we assign costs to these instructions. So we have defined these in a file like this. Here we can see an add with 16-bit variables takes, we assign a cost of 3.25 to it. In addition, here with 32-bit, we assign two clock cycles. So we assign 2 clock cycles to it. With the FP, we mean floating point. So this would be 32-bit float data type, also 2 clock cycles. So how do we get these values? Well, these values were measured on the hardware. So we basically run a special program that executes a lot of these simple instructions in a specific way so that we can get an average value of how long it takes to perform this kind of operation. We do this with compiler optimization O2. And as these are statistics, usually this number is not, so this number doesn't always have to be a simple number. So yeah, 2 clock cycles for one addition sounds reasonable. So for a specific target platform, this also might contain some kind of memory access. So 2 clock cycles is a reasonable value. But it also, here we can see for the 16, 3.25, well, for 16-bit, there is some additional overhead to get the actual result from the 32-bit data that was generated. And depending on how often it is done, there is a bit extra here. And this takes at least to a certain degree into account that there was a compiler optimization available. We can also see here with the at64 floating point, 206. So this is a cost that sounds quite high compared to the other values, but this target platform doesn't actually have an actual processing unit that can directly work with 64-bit floating point data types. So this means this 206 reflects software emulation. So the hardware basically has to do several steps, so several calculations, one after the other. And then, yeah, this takes a lot more time than using the processing directly. And yeah, in this example, I don't have any values below 1. So in some cases, we can even see 0.5, for example, for an addition. This would mean that, yeah, the hardware has multiple execution units. It can basically execute 2 of these additions in 1 clock cycle. The advantage of using this kind of estimation is that it can be done very quickly. We have to go through the C source code, and we can do this even if the source code is not fully complete or executable, and we can just add everything up. However, yeah, this is not that accurate. So typically, this estimation is around twice as high as real measurement on the hardware. And the key point here is this compiler optimization. Although we are doing these values here with compiler optimizations, we cannot take into account what is actually executed on the hardware. So even for a test case like this, so we have 4 loops, and here the inner loop is executed 4 times. Well, that's only if you look at the C code. The compiler might decide to perform some kind of loop unrolling or other optimizations. So loop unrolling for a loop with only 4 iterations would bring us the benefit of getting rid of this comparison or getting rid of this addition. So doing this a couple of times here will already reduce the runtime here. So with the C code analysis, we have to assign costs for that, but this cost might actually not happen on the actual platform. That's why we have other options. The second option is to use the LLVM IR. So this is quite fast and quite accurate. The idea is that the LLVM compiler suite provides an intermediate representation. So here I have a screenshot of how this looks like. Basically, we have different operations, or here there are a lot of function calls. So this is a representation that is used inside of the compiler, and it is the representation after at least some compiler optimizations were applied. So the normal compiler optimizations for the target platform, but not necessarily for the target platform. The optimization I mentioned before, so the loop unrolling, getting rid of loops that are not really required, this can be done without any knowledge about the target platform, is usually helpful if the optimization here needs more memory later on. So if at least enough memory is available, then this kind of optimization would be applied. And yeah, going through this code is basically the same. We can assign costs to each instruction that is mentioned here, and these costs can come now from data sheets or measurements, because these are more closer to the actual hardware. These these values can already be extracted from the data sheet of the hardware. So this is definitely more accurate because it uses compiler optimizations, but still has a bit of a limitation that it cannot take into account special optimizations for the actual target platform, because the special optimizations are usually applied after this. But with this, we still have a way to improve the first C code analysis with additional information. Now, our third option here provides the best solution. So it's analyzing the assembler code. So it's still, everything is statically done. So we are not running the code, but we compile the code. We generate the assembler code, as seen here. And if we have the assembler code, we can see the different instructions that are executed. And we have some additional information here. We know which kind of pipeline is used for it. For example, here, this multiplication is running on the integer pipeline. This operation is running on the load store pipeline. And we have some additional information about the latency. This means how long does it take to be executed, processed inside of that pipeline. So the multiplication here, for example, needs 2 cycles. And with this kind of information, we can model the processor pipeline and assign these instructions to pipeline stages to model the timing of the actual execution. The advantage of this assembler code here is that really all compiler optimizations are included. So if there was a loop here, this is already flattened. We only have basically jump instructions to specific addresses if something of that loop remains, but might also be that but also other compiler optimizations that are not included in the LLVM IR, like using special instructions here that might optimize it. So instead of having 2 or 3 LLVM instructions, it might be a single one that the hardware provides. So this has really the advantage that we get a quite good accuracy here. So we can reach an accuracy of around 90 to 95% compared to measurement on the hardware with this approach. Some small disadvantages here. So it takes a bit more time for compilation and calculation because we really need to compile it, and in order to be able to track everything back to the original code, there are also some internal transformations required, so this takes a bit longer. And yet sometimes this tracing back is not completely possible because the assembler code really tries to remove everything that is not needed. So going back to the original C code might lead us to cases where nothing is left from the actual C code. So this means the whole approach has a small, well, I would say unsharpness. So in some cases, the actual performance gain might be in the code in that area. So if we only look at function level or broader structures, then this doesn't matter. So we get performance numbers that are good on the higher level. On the lowest level, it might be overlapping with the code, might overlap with the code right next to it. Now, in order to judge the quality of results, we also have introduced our own metric. The issue is, if we don't have the execution frequency for everything, then we have a certain degree of uncertainty inside of the program. So what we have defined here is the metric of confidence. Basically, is defined as the minimum execution time divided by the estimated time. So with the minimum time here means we look at all unknowns that we have inside of the program, and we treat them as the minimal number. This means if we have a loop, we don't know the number of executions, then we assume it has 0 iterations. So it really has a small impact. And for the estimated case, we usually take then the specified default value. So for a loop, it would be 10, for example. So this means we already get a difference here. And with this difference, the confidence usually is smaller than 1 if we don't know all the execution counts. If blocks is a bit less critical. We basically can analyze if blocks, and we have a duration for the true block and the false block, or the true path and the false path. And for the minimum duration, we can just take the one that has the lower impact. So this so if an if block is unknown here, the actual impact on the confidence is not as high. It's basically just the difference between the timing of the true and false path. Yeah, as I already mentioned, so 1.0 or 100% means that we know the execution frequency of all blocks. Everything lower than 1 means that there is a certain degree of uncertainty inside of the estimation. And yeah, 10 and 50%, I already mentioned that. So the benefits of this approach is that we can really do it very early in the development process. We can even provide here ways to do continuous monitoring of the performance changes. So you can track how the performance changes during the development. So if you make changes to the source code, what is the impact on the actual timing? You can also use this information to check how the performance is different on different target platforms, even heterogeneous ones. So with this approach, we can have combinations of different processing cores available. So that's all that is possible. You get detailed information. High runners or the critical parts of the software application can be detected very early on. So you know where to focus on if you want to optimize the performance or if you want to analyze the worst case timings or the critical path. And this estimation also helps with the core utilization in parallel applications. So what are the limitations? So basically we have two topics. The first one would be that we only use abstracted hardware, but no actual simulation here. So this means we don't execute the code. So we cannot really take into account anything that is basically information of the whole system. So something like runtime of signals. So this might be bus systems, network, all peripherals. These cannot really be analyzed statically because this would require knowledge about the whole system, and this is not really part of the actual source code of the application, but is part of the hardware description. This also means, the timing for memory accesses. So if there is also some contention on memory and something running in parallel, we can only provide simple numbers for these memory accesses. And all that means if the timing of the whole system is more of interest, then this whole static analysis might not be the best way. Another thing is coming from the software side. All dynamic effects from the software are also hard to analyze statically. This means the impact of the operating system. So if there are some decisions to schedule other tasks or to move some calculations around, this impact cannot be taken into account, as well as other interactions between tasks. So basically, same thing with the hardware, but on the software side. So we cannot take into account the effects of the software system level here. Now, a short, a final chapter here, just how can we integrate that into a workflow? We provide here different ways. A very typical case would be integration into a continuous integration workflow. The idea is you have a CI workflow set up, and you can add this run code analysis part to it and automatically analyze the runtime during a normal CI flow whenever some changes to the source code were done. So you can basically track changes over time. So how can this look like? So you can basically get reports like this. You can see, there are different functions. You have average, min, max time. So you can track all these numbers. You get a list of unknowns. So what kinds of blocks or parts of the source code cannot be analyzed, and you get all this information automatically after any changes to the source code were done. And yeah, with that, you can also use some kind of monitoring report, as we can see here, about the function here, just an example, perform calculation. We can see with a change here, with this change to the source code, we can see, oh, suddenly we have a much higher time, and we can identify the commit that really changed the actual timing. So I think in this example, it was just a small change of changing the data type from float to double without thinking about the target platform. And suddenly, yeah, it's more than 6 times, it was more than 10 times even, the runtime difference here. So you can identify this kind of cases. For the developer, we provide this graphical representation. So if you have the continuous monitoring and see we have a case, oh, there might be an issue with it, then we provide this hierarchical visualization. The idea is the width here corresponds to the actual runtime of the block, and the y-axis shows us the structure of the program. So basically, we have here a function. We can see here if blocks, function calls, and yeah, in this example, there are no loops, but all the different control structures that might exist inside of the program. And we have some color highlighting. So this orange here means these are constructs that we cannot analyze statically. So we cannot estimate if the true or false path is taken here. Okay, that was all about the theoretical part and the static performance estimation. Now would be time for some.
Okay,
so
this is start recording again.
This is now the representation inside of our program. So this is only the performance estimation part. So we're not looking into parallelization or testing everything that is minimized right now. Our test program here is a simple example. We did run some obfuscation on it. This means, yeah, variables always start with var and have a cryptic name here. Same goes for function names and other types and stuff in the source code. So this was an actual use case, but hopefully here we cannot really see what happens anymore. Now, how does it work? What do we do? What do we need to set up a project here? So basically, we create a new project. We copy all source codes that are required. So we have this main source file, and we have a couple of includes. So these two includes are coming from us. So this is just because we have developed that code, but we are only focusing on this one C code. Next, what we need to do is we need to define what kind of performance estimation we want to do. So let's start with the C source code. And finally, we need to define the root function. So in this example, we just have defined the main function. Basically, we need to define the entry point from where we want to start with our performance estimation. Let's generate our hierarchical program view here. So now it's just doing the C source code analysis, basically analyzing everything by looking at the C source code and generating our graphical representation, and we get this kind of representation. So as I already mentioned, X and Y axis, we can see the root function at the bottom. So here we can see the main function. If we go higher up, we can see here different loops. We can zoom into it. So here a loop with 12 iterations, with 15. For all of that, we can also have a look at the code. So if I click on something, I can see directly the corresponding code. And we also have one orange case here. If you have a look at that, we have here an if. Okay, the question is if this variable is bigger than 0. Okay, if we cannot analyze it using constant propagation, so we don't know if this condition is true or not, can see then here, then 50%. So we assume that the then cause is 50%. We can also see the else path or the false path here with 50%, and we can see there is a big difference between them. The true path here is assumed with 390,000 cycles, and the else path only with 5,000. All of that is done here for the current platform. So I have selected an Oryx TC397 starter kit here. Now the basic runtime ratio is here. Oh, no, the basic estimated time would be 2.4 milliseconds using the C code as basis. Now let's switch it to a different method. So let's go right into the assembly estimation. So just doing our performance estimation for the assembly code. If we look at the console, we should see some additional steps. So the topic that it takes more time is not as relevant in small examples like this. But if you go to larger projects, you will see there is a lot more difference between it. Now we see some additional messages here. These are warnings about the matching, what I already mentioned. There is a certain degree of uncertainty. So at least it's not always possible to map the assembler code to single instructions. So this is the mapping on instruction level, but on block level, this is usually high enough. And we also, well, this is all the map, complete report here about the mapping here. And we can also see that this was compiled. Where was it? So here we can see there was an actual call to try call GCC. So this is defined here in our settings. We support several compilers. For example, here for Oryx, we are using the high-tech GCC compiler. It will compile the code, and we use that as the basis. Now, how does it look like if we look into our graphical representation again? You can see the number is now vastly different. So we have 1.05 milliseconds. As I mentioned, usually you can expect around factor 2 between these two results, just because the compiler optimization usually can apply or can improve the code by this amount of, by this factor. If I just click on that block, we had the number before, more than 300,000 cycles, now in the range of 150. With the assembler analysis, we can also have a closer look at what was actually used for the estimation. So we can also look at a view like this. So if I select a block down here, you can see, okay, in the C code, it is this part of the code, and this shows the results of our matching. So these are the instructions that belong to the actual loop here. And as already shown inside of the presentation, here we can also highlight what kind of information is used for the performance estimation. The results are not only shown in this way, we can also generate a performance report here. So the performance report would be here an HTML document, can of course also be opened in another browser. And here we then have a list of all functions that were analyzed, together with how often were they called, the estimated time, as well as the confidence we had. So for the confidence, most of it should be 1.0. Just by looking at this, we can see there is not a lot unknown in this application, but this one is. And we can see, the impact usually here, there is then a 0.9 or 0.7. So there is an impact here about not knowing how long, which decision is taken. In some cases, even lower. This 0 here, we will change the representation. Basically, we have a function here that has an estimated time of 0, which will always lead to a confidence of 0, but actually confidence should be either not available or 100%. So a function that is empty always has 0, and just by the way we analyze it, it would be defined as 0. Now, how can we improve this number? As I mentioned, we can provide this number, but yeah, the best way, if we have a code that can compile, is to perform profiling. We have directly integrated profiling of C code on the host into our tool. This will basically compile the code and execute it on the host platform to get us the number for these unknowns. It's basically just enabling this option. Then I get this new profile on host. If I run that, it should execute another compile step using Clang. Here we can see missing, okay. And we can see here some additional Clang codes. Now we have additional information. Run our performance estimation with this additional information. And see what the result is. So simple true, simple if else should be a bit different of a different result then. Let's see it. Where is it? Oh, takes a bit to open. Oh, now it's building graphs, and now we can see the orange part is gone and the runtime here is a bit higher. What we can see here, okay, then 100% then. This means our profiling now analyzed, found out that this condition is always true. Well, if we have a look at the code, we can see there is a for loop here that is executed only once. So basically, the question was only if the if block is true or false. So here we don't even have some kind of percentage. But if we would have a loop here that was running multiple times, we could provide here relative numbers so that, I don't know, 20% of cases it is true and 80% is false. But if we only have a single execution, it's basically only the question whether it is true or false. Now, all this performance estimation here runs on our own internal platform description. The idea is that this can be used to extend different target platforms. So here, for example, we are using the starter kit here in this case, and it's using this microarchitecture. So all the costs we use for the actual performance estimation is provided here in JSON or JavaScript files. So this one would be the simple one. Yeah, if we look at the C source code, this one is the assembler code. And just the way we provide it, it means we have here different text files, and you as a user can modify this or create also your own target platforms. So defining just a new processor, assigning some costs to it, so extending it to different platforms that are behaving at least similar to what we already support is not a big deal here and can be done. One additional thing here is also there is one file for the function calls. So all function calls that are inside the program that are treated as black boxes, like printf, memcopy, stuff like that, can be modeled here inside of, or can be described in this file. We can either assign a single value as cost to it, or we can even provide some kind of function to model the timing behavior of that. So yeah, for memcopy, of course, it somehow depends on the parameters of the memcopy, so about the actual size that should be copied here in this example. In the performance report, we provide also a list of unknowns that were not taken into account here during this analysis. In this example, we can see there are some floating point implementations from math library that were not, where we didn't have assigned any cost. So fixing that would only means that we need to provide the numbers here. So what you need for that is basically either the hardware or a typical case. So for these ones, we can basically extrapolate these values also from measurements on other platforms. And yeah, we can also see the one if block that had the highest impact that we could see directly with the orange representation is here in this representation. We see there are some other if blocks inside of the code that were not analyzed, or that could not be analyzed statically with our profiling